what we will now onwards do is we will come out of that piston in a cylinder situation. We will go to open air, okay, and then we will see how the sound is generated first, and then we will see about how it gets transmitted. Now, the simplest source which can generate a sound and simplest to analyze is a sphere, okay, which we can why it is important also is we can shrink the size of the sphere so that we can call it a point source. And why that is important? Because point source can be clubbed together to make a extended source. So, with some subtleties, but roughly that's the idea. So, for that what we will do is see we had so Laplacian of P is 1 over c square by dt square. So, we will write that in spherical coordinate system because we want to use a spherical source. Okay. Now, and source, when I am using the word, what I mean is some region in space which is in contact with my medium, for example the air medium here, and which is capable of continuously giving some energy as a function of time. So, that is how I mean when I say source, and here there is that means there is a spherical region which is in contact with the medium, and from there I am able to give energy out. So, now I can write it the full form 2 over r, though we are not going to use all of them, but just to see that how they look like, nothing else. Sin theta theta of theta plus okay. So, this is the full equation, but what we will do is, because there is a sphere and we are assuming that the sphere is getting expanded, compressed, not sinusoidally for now, we will come to that, but for now it is whatever is happening spherically symmetric happening. Okay. So, then just these terms will make no contributions. So, we are left with only this. Okay. Now, that means our pressure P will now be a function of R and T only. Okay. Again, it has become one dimensional, but in a spherical way, not a plane wave form. So, we have come out of the plane wave situation now. Now, many results which we had derived for plane waves now will not be valid. So, P is a function of R and T, which will satisfy this equation. Now, to solve this, what we can do is this part we can write I want to use a different color. This we can write as this 1 over R sorry, just check if you can write or not. This will bring out two terms. First differentiation will bring two terms. You can do that. Okay. And then once you apply, the first term will have two terms again, which will create this one dp over dr will come from first term, and the other dp by dr will come from the other one, and these two, that's why it is coming, and The first term is d square p by dr square, that is here. Okay, so this portion is equivalent to this, and then here this p, if we write or substitute as rp, no harm, because r is just a coordinate and differentiation we are taking with time. So this is not going to change in any ways. This term, if I replace p with rp, will that differentiation with respect to time change? No. So I can always change that, okay, without affecting the equation in any ways. That means this will now become what? Something is something somewhere is that r will come from there actually. Just check that. One factor of r will come, and which will actually get cancelled with this. Just a minute. This, if I substitute this, it will become what?
Divided by r. If we are replacing that by r, then it should be divided by r. Then it will get
Yes. So you have to, sorry. You have to, because to keep it same, you have to rc square d square rp over dt square, right? Now if you equate them, so you come to the point where you have d of d square of rp with respect to t square, which is, I think, this one, this part will be equal to c square times d r square, right? So, and this equation is exactly the one which we had solved earlier. Okay, so only change is in place of p we are having rp. So that means now we can say that rp can be represented as some function f1 with okay, ct minus r. It will okay, you think about this, in which direction it will move, right? We had such solutions earlier. If rp is just the variable, okay. Now and then which one of this is going out and which one is coming in? This one is a diverging wave, right? It's going out, and this is coming in. And so from here we can actually write like this. So this r we can actually multiply over here. Fine. Now what it tells you is there can never be a physical source of zero size. Means any physical source which produces sound has to be of finite size, otherwise this will make pressure infinite. This is 1 over r. Okay. And one more thing, we are going to study about our main aim is to study the radiation of the sound, or the generation of the sound as from a spherical wave. So we are not actually concentrating on this part, which is actually converging onto the sphere. So for us, another way you can think is the sphere is placed in a environment which is completely radiating outwards. There are no surfaces which are reflecting anything back. So no wave is coming back, whatever is going is just going out. It is equivalent to saying that the tube was infinite or an infinite string we had, right? Whatever we did on one end, it was just going through. Nothing was getting reflected back. So that conditions equivalent is saying that we are not taking this into account. So for us, this much is the pressure field. Okay. Now, if that's the pressure field, there is one observation which you can make is in plane wave case, whatever shape you had of the pressure fluctuation, it was moving with speed c without changing its shape and size. That was the meaning of this. At that time, this 1 over r was not there. So it was just moving. Now in spherical case, same shape is there, just the size is getting reduced as you go farther and farther. So that's the difference from plane wave to the spherical waves. Okay, because as you increase r, the amplitude is getting reduced, shape is not. This is giving you the shape of the pressure fluctuation. It is remaining exactly the same, but the amplitude is getting reduced. And there is a general rule again. If you are solving wave equation in odd number of dimensions, then the shapes will remain same. And one more thing, suppose you have a 1D domain like that and you sent a wave fluctuation. Now suppose you are thinking about a point here P, till the time the wave hasn't reached this, it will be stationary. Then once the wave is going through, it will start moving and it will have the same shape. But once the wave is gone, this again is back to its original condition. If the wave is gone, suppose you think of a pulse, okay, a wave pressure pulse which of this shape, it has gone, just it will disturb it, it will go. After the disturbance is gone, this is exactly in the same state where it was. This will happen in plane wave case also, in spherical wave case also. The difference being only that if the P is here, it will be less disturbed. That's the only thing. What is same in plane wave and spherical wave is that they will get back to their original conditions once the wave is gone. But if it is a 2D surface, if it is a 2D wave, this is not going to happen. Both the shape and size will change. As they move in 2D, shape also will change, size also will change, and this point will never come back to its original. This pulse will go, leaving a wake behind. It will leave some effect forever. It will never come to, practically it will come back because damping will be there, it will be reduced, but theoretically its effect will be there forever on this. So, and then that is true for any even number of dimensions, 2, 4, 6, etc. In odd dimensions, the previous thing which I said will happen. they'll come back to their original form, state. Okay. And yeah, so that's a fact. Okay, we'll stop here because then we will get back to sinusoids. We will see then in the next segment what we are going to discuss is if we have a spherical source with certain strength. Generally sources are expressed in terms of their strengths. That means how much flow per unit area they are capable of producing, flow density. Okay, so in terms of that we will express the spherical source, and in terms of that we will derive for small sources we will define what is the meaning of small source, big source. The term k times r will be a very crucial parameter, okay, to define whether a spherical surface is small or big with respect to, and then we will see the impedance of such spherical waves. Earlier the impedance was just rho c for plane wave, right. The characteristic impedance was rho times c. The pressure times velocity, pressure divided by velocity was always that constant, right, rho times c. But here we will see that it will not be so, things will be complex, and then everything will come from this expression and the boundary condition that the spherical surface moves at a particular function. So from there you will see that why small objects cannot create big sound. Means if you have to have a speaker which produces large sound, you have to have a big speaker. So those are the things which will come out of this equation. So that we will discuss in the next segment.